One of the powerful capabilities of pointers is being able to perform arithmetic operations on the pointers. Now, this is a little bit different than what you might think, because these math operations will be scaled according to the pointer's type, to what the pointer points to. If you add 1 to a character pointer, it will move the address that is contained in the pointer forward by 1. It will add 1 to it because it points to a character. If that pointer is an integer pointer and you add 1 to it, the address, in our case, in our machine, the address that's in that pointer will be adjusted by 4, the size of an int. If it is a pointer to a short int, it will be adjusted upward by 2 bytes, or just by the number 2. And that's just a simple increment. Now, when you do this, you have to be careful not to move a pointer off the end of what it points to. If it points to an array of integers or characters, some assembly of these things, then you can't go incrementing off the end of that, or you'll cause an error. But pointer plus plus, minus minus, all of the integer type math functions will add the size of the pointer's type rather than simply increment it. Now, you can't add a float or a double to a pointer and do things like that, because that doesn't really make any sense to a pointer. But you can do basic arithmetic operations and manipulate pointers, and you can compare them to see if there's a number of objects in between 2 pointers. If 2 pointers are both integer type pointers and you subtract one from the other, you will find out how many integers there are between them in memory, so you can see if you're moving your way through an array. Let me take you out here and show you a piece of code that actually 1 character longer than this in storage. What is this, 10, 11? It's actually 12 bytes long, and it's that same little array that we showed earlier. Here we have a character pointer, star AP. We set it equal to A, and we know that A, without any subscripts or anything, is in fact the same as the address of the 0th element, where this H sits in memory. So we've created a character pointer, set it equal to the beginning of that. Here's just a little counter, I. And what this thing will do is while contents of AP, that means while that is returning a true value, non-zero, remember there's a 0 there right after the D, while that is valid, non-zero, print it out. And what I'm going to print is in uppercase hexadecimal, %x, and then a character, %c. I'm going to print the pointer itself, AP. That's going to be the memory location, the address that is stored inside AP, and then I'm going to print star AP, which is the contents of the memory address that is inside AP, and that will be our character, HELLO, so on. Then I will increment the pointer, AP++. So I increment AP, so first it'll start at H, and then it'll go to E, incremented, then L, and we'll work our way down until it increments to point to that null, and then this while will fail. Now, after that while is done, we will come here and start a new loop. I'm going to set AP back to the beginning of A, or the address of A. There you see that, the address of the 0 element. So we start over again, because AP has incremented its way out to here, so I'm going to set it back to there. Then I fix up I to be equal to 0 to make sure I have a nice clean counter. And as long as I is less than 20, I just stuck a number in there that I know is bigger than hello world, we will set nulls into the contents of AP plus I. That's our pointer plus our counter. The contents of it will be set to null. So we're going to progressively wipe out this string with nulls, and then we're going to keep going someplace out here in memory. Well, it's not really out there, of course, but when this thing is compiled, hello world has a known location, and the operating system knows that we're messing around and going farther than we're supposed to go. Some operating systems know this, others may not. And this is a good way of corrupting large tracts of land if you don't know what you're doing, and if you're not careful about little subscripts like this and running off the end of memory. So let's run this thing, pointer.c. And I'll show you what happens in Windows when we do this. We compile and link it. There we go. It's compiled up, and then we run it. And there's our hello world, and now it's running off the end of memory. And this is what happens. Pointer.exe has encountered a problem, needs to close. Sorry, I'm sure you've seen this before, but this window is what happens when a program does something it's not supposed to do. Now, we won't go into all the debugging and all that, but if you have, and I know that you have installed your compiler. Your compiler comes with some debugging capabilities, and we could enter into debugging and see what's happened. And basically what we've done is we have stepped over a boundary. A bounds checking of the operating system has kicked in and protected us from ourselves and stopped the program. In older versions of Windows and other operating systems, the bounds checking didn't occur and you'd crash the whole system because you could potentially run off into parts of the operating system, other programs, wherever you're not supposed to be. But the current